everyone, and thank you for so much for being here. My name is Sirko Höer, and I work at the German Federal Office for Information Security, short the BSI. And before I started this job at the BSI, I worked at Code Intelligence as a security analyst beside my studies. And my main work are the analyze of open source projects, for example, Suricata. But I analyze many other projects. And I'm going to talk about my experience about fuzzing of large projects like Suricata. First of all, I would like to send a big thanks on all persons who are involved in this process, because that's the whole process of analyzing and security things on Suricata is taking nearly 1 year. And especially I will say thank you to Robert Heist, I hope he's here, our contact person, to DCSO, and Victor Julian, he is a lead developer from Suricata. And also a big thanks to the founders, Henning and Sergey. The last thing that I mention is a short disclaimer. I speak here as a private person and not, I speak not for the BSI itself, and all methodologies that I mentioned here reflects my experience about fuzz testing and not the general approach how fuzzing is used by the BSI. That also the same to my opinions about fuzzing. And that's my opinion and not the general opinion of the BSI. So let's start. Basically, there are two main parts that I will cover in the talk. First, I talk about my methodology and my approach, how get into the fuzzing with Suricata. And the next big issue, or the next big talk is, or the next big topic is I want to show by an example what kind of bugs I found in Suricata, and I found many bugs. And the last thing, I will conclude some things. But before I go into detail, I will start with a short introduction. What is Suricata? Suricata is, in one sentence, an open source intrusion detection system and intrusion prevention system. And what is an IDS or IPS? For those who are not familiar with it, is an IDS is an analyzer that analyzes the local network and reports malicious behavior in this network. And it develops by the Open Information Security Foundation and has many developers. I think over 60 people are developed for Suricata. And the main language that are used for this program is C, and part of the parsers are also written in Rust. That's very new that the parsers are also written in Rust in Suricata. And as I mentioned, I started the analyze of this project in the year 2019, and at this point, Suricata uses only unit tests and AFL fuzz tests to check their functionality and reliability of their code. Nowadays, they use OSS fuzz by the help of me and a lot of other developers. And at this time, I decided to start fuzzing Suricata with the fuzz engine LibFuzzer. Mainly, in general, a pen tester has three. The process of fuzzing projects consists of 3 parts for a pen tester. So the first step is the setup process. Matthew told us that the setup process for the students are so big that they don't really have time for analyze these projects. And in my opinion, setup process is in every project. The setup process is every new and every difficult. Several build systems are out there, and every build system has the dependencies, for example, compiler versions, and so on. The second step is analyze the project itself and write the Fuzz target. And this, the third step is to run the fuzzers and report bugs. And reporting the bugs is also a big and huge problem, because developer has responded these bug reports and has to patch this. So only this process is a huge, causes huge time. So I start with a setup process. Suricata uses for the build system the normal automake and autoconf build system. It's a fairly old build system, I think. And the advantage of this build system is that I can very easy pass build flags through this build system. So I created a build script, and this build script contains, for example, the compiler. I use clang, of course. I use libfuzzer for the fuzzer, so I need Clang as a compiler, and I also need these flags, compiler flags, like sanitize, address, and fuzzer no link, and some other addition screws to adjust the results of fuzzing. The third big thing for the build process and make fuzzing possible for this project is that I have to patch the suricata.o, that object file, because the normal build process is so that all object files are linked together to one executable, but I need for the fuzzer only the library and not the executable. So I have to patch this main out because of naming conflicts. The fuzzer brings their own main with it, and while compiling the targets, we have a naming conflict that's bad. So I patched it with a simple sed command. And also, I packed all object files to one archive file because we have over 600 object files. The next step in my setup process are I create a Docker file to install all dependencies and make a clean environment. That's nearly the same that Google's OSS Fuzz does. And the last step of my setup process is to build my own makefile to combine all commands and to build the fuzzers itself. The next and more time-consuming thing is, of course, the analyze of the project. And we have here over 600 source code files, and it's very hard to get into. So at this, at a person who analyze projects, it's always a good thing to look at the unit tests, for example, at the first time. Or it's also a good thing to look at the existing fuzz texts. At least it is good to know how the entry point is, and in which file the main function is located. So you can trace this path to this program, for example. And it's always also always a good idea to look at the bug tracker and to see what kind of problems are there currently, and use this knowledge to create some other fuzz targets. For Suricata, I use the entry point suricata.c, and in the folder source tests, there are a couple of tests, not all. Sometimes the tests are located in the functionality source code. It's bad practice, but they rearrange this this kind of structure every day. So at this time, I use these entry points to look at this project. So take a look at a partial look at the suricata.c. It's over 3,000 lines of code, or maybe more. I don't remember how many lines that was. And nearly in the middle, there are some defines for AFL fuzz. I know that, and I look at how they created their fuzz tests, and there are about 24 and 25 written targets at these days. Nowadays, there are 39 targets, and they cover some parsers like HTTP or SMB or SMTP. They are also cover the low-level decoding thing, like an IPv6 or IPv4 decoder, or the PPP decoder, or in this example, the Ethernet decoder. Some other low-level protocols are also decoded. And because of their many targets and their many APIs, I concentrate in the first step only of 2 API functions, the app layer parser and the decoder parser. And for this, the developer implements some other functions, app layer parser request from file, for example, or rule parser data from file. So these are self-implemented functions that uses AFL loops to read some buffers from a file and to put into the engine. So to write a Fuzz target for libfuzzer, I adopt the initialize code. It's very easy to find out which code it's necessary to initialize the libraries. So that's a very easy step. The more complicated step is to go into these app layer parser from file, etc. functions and pick these types of code that are necessary for my test one input function for libfuzzer. And the final step is, of course, pass through the data from generated from the libfuzzer generator, from the mutator, through these app layer. So basically, there's about 150 lines of code per target, and it's not a one-liner, so to say. Sometimes we have projects with one-lining code or with very easy to set up. We only have to initialize one specific object, and this object has a method, and this method is used by the parser, by the fuzzer. In this case, I have a lot of structs and a lot of variables that has to be initialized before I can run this API function. And that is the thing that makes Suricata so complicated. Because they also fuzzers can produce false positives if you don't focus on this initialization. That's a big point at this point. Yes. So to conclude this, I reused code. That's not bad. In every project there are unit tests, and in unit tests you can use this code basically to initialize your things in their Fuzz targets. And yeah, you have to customize it for a general Fuzz target. The other step not only the writing of the Fuzz target is a problem. You have also think about the seeds and the dictionaries. For example, if you have a parser, you need a dictionary, which keys and values or which keys you expect for these for the fuzzing process. And it's also the same for a network parser. I generated a dictionary of known values for network protocols, and I use some seeds that I dumped while with TCP dump, for example, and then I run these fuzzers. And then we come to the third step, the run fuzzers and bug tracking, and I will show you an example what kind of bugs I found in Suricata. It was a bug in the Ethernet decoder. It is a heap buffer overflow as a read. That means the program tries to read some memory region, and they are not allowed to, or it's not the right area to read this. And this bug will lead to a crash of the program which is bad. An IDS system has to be online every time to filter and to analyze the network. And if I have a method to crash or to DDoS this program, then that's bad. And short recap, Ethernet packet is part of network frame and consists of metadata like destination or source address and the type. The type is very important at this time. And the payload. And the payload consists, for example, other layers like IP or TCP. And this is a reduced I reduced the complexity of the code and make some pseudocode. So I hope you are familiar with it. We have the original input that consists of 6 bytes destination address and 6 bytes source address and the type. And depending on the type, the switch case refer to the specific case and execute the instruction in this case. And if I modify the payload in a way that the first 16 bytes and repeat these first 16 bytes n times, so the decoder Ethernet function will called recursively each time. So, and I manipulate these payloads in a way that at the 5th iteration the type is missing, but in the first 4 iteration for Suricata was a valid packet, and in the 5th iteration they looked for a type and there is no type, and then the program will crash. Maybe, or they will crash if the sanitizer is on. What do we found? Complete. We found about 14 bugs in a time period of 1 year. So these 14 bugs consist 12 bugs of these 14 bugs are security related and correspond to a CV number, and all bugs are patched in the current version. And most of their bugs are heap buffer overflows and memory leaks. And one of the biggest issues were at the SSL parser. That was a write buffer overflow, and I had a potential to manipulate more than 600 bytes of raw data, and this was a very critical bug. To conclude this talk, I will want to talk about, in my opinion, the big plus of coverage-guided fuzzing. I get in contact with coverage-guided fuzzing while my studies 2 or 3 years ago, and I think coverage-guided fuzzing is the fuzzer engines like libfuzzer or hongfuzz or AFL perform very well against parsers and decoders and image parsers, and they are coverage-driven. That means the fuzzers want to make it possible to get a highest amount of coverage while testing. It's like a deep search, and it's scalable and really fast. Scalable means we can run multiple times on multiple servers, and you can test your projects very, very fast. But what can be improved? What can be improved is it's sometimes very difficult to set environments, essentially for grown projects. Projects that are more than 15 years available on this planet, and sometimes the build systems are self-written, or sometimes the build systems depends only on GCC or only on GCC at a certain version. That makes the implementation and the setup process for fuzzing much more harder than I thought. Also, I think that you need a deep knowledge of C and C++ if you fuzz C and C++ projects as a pen tester, and you need also a deep security knowledge, because if you found some bugs, you have to know how to avoid these bugs. And if you don't have the knowledge about these security issues, you don't know how to avoid this or how to patch this. So that's one of the next big things. And then the other one is that structure-aware fuzzing or socket fuzzing or state-dependent fuzzing has to be handcrafted, handmade. It's not a built-in feature for these fuzz engines. And also a big issue is how to fuzz smart devices, IoT devices, which normally uses another architectures like ARM or MIPS. So I'm at the end of my talk. Hope you enjoyed and hope I'm not too fast. So if you have question, I can answer you this question.
So Sirko, can you hear me?
Yes.
There was one question asked in the last.
Yeah.
What configuration do you run this fuzzer? And how long?
Can you repeat, please?
The internet connection is not great right now. What configuration computer did you use to run this fuzzer? Also for how long?
I use certain configurations. I hope you mean that which options I use, for example, right?
I think more like the hardware. That sounds like a hardware question. Maybe.
So more the hardware. Yeah. First, I use a laptop with 4 cores and something like 32 gigs of RAM, and I run these fuzzers on our server for about 1 week per each Fuzz target.
All right. You mentioned that in the 1 year you found 12 CVEs. Was the fuzzing running mostly non-stop for 1 year? Or
no.
How many fuzzing systems were leveraged for this?
No. The fuzzers runs not for a year. I analyzed this project not full time 1 year. If I had time in the studies, I go to work and I analyze sometimes 8 hours a week or sometimes 1 hour a week. So if I have time for this, I'm investigate the analysis, and I run the targets only for a week, sometimes for 2 weeks, and this is one of this most. This is one of the challenges. When is the fuzzer? When has the fuzzer found all things, or when it is done, so to say, and. Some opinions say that if you reach a certain coverage, then it's done, and some others say when this fuzzer is run for n times n hours, then it's done. So I think the probability that the program has nearly no bugs is more likely if you run the fuzzer longer than 1 week, but that's my opinion. Yes.
Another question. How long did it take? Tomasz is asking, how long did it take to prepare fuzzing harnesses? The fuzz targets, I guess.
Yeah, it's depend on the fuzz target. Yes, I start with the low-hanging fruits. I see the AFL fuzz targets, and the conversion to the from AFL to the fuzzer takes 1 hour, for example. But I used it as an example and write my own fuzz targets, and that takes sometimes 8 hours, sometimes 4 hours. It depends on if you have compiler errors or linking errors or reference errors. I hope that answers the question.
Yeah. Also, you've done a lot of work in Suricata. Would you say your work is complete, or you're still like working on it, fuzzing on it?
I continue to work on the fuzzing today, but I do it in my free time. And if I have time for this, I implement some new fuzzers, but I'm already in contact with the security, the head of security of Suricata, and we develop both together new fuzz targets.
Yeah, I bet you both know each other quite well right now.
Yes, that's right.
Okay. Are there any more questions from the audience? The Slack is silent. Also, the Click Meeting chat is silent. And we have still 2 minutes to go.
I'm pretty fast for the talk.
Yeah.
Yeah, okay. If there are no more questions, we can continue. Thank you, Sirko. It was really interesting and informative. And have a good day.
Thank you.
Enjoy the rest of the conference.